Thank you very much. Je suis très heureux d'être ici et d'avoir la chance d'améliorer en français et de parler avec vous au sujet de cosmologie et fromage, bien sûr. Obviously, the whole talk won't be French because that's basically as much as I can do before I get nervous. But thank you very much for having me. It's really great. And I wanted to talk to you about a few topics in supernova cosmology, and particularly in the photometric era that we find ourselves in. And the reason why I gave such a kind of broad title is partly because we've been hearing a lot about applying methods to different areas and different subject interests. And I think it's really important as we do that to learn about what each subject cares about and then how we can make the most impact. And as someone who didn't grow up thinking about supernovae, but grew up thinking about potentially the statistics of supernovae, I've had to learn a lot of this. Also, since we are claiming nationalities, Descartes being Dutch, I wanted to remind everyone that Krige, which is the person that Krieging was named after, you have to add the Dutch G to the pronunciation. He was South African. So anyway, I just added that slide at the last minute. Okay, so I'm going to give you this talk as a representative of the LSST Dark Energy Science collaboration, particularly the supernova science case, but I'm interested in desk science more broadly, and motivate why this is important. Now, I know a lot of you in France are in LSST, so you're all getting very excited. But one of the great things about the, let me make this a bit brighter, then I can see as well. There we go. So LSST is about to have engineering first light, well, about to, it's 2019, with operations going to begin in 2022. And I thought I would give you this tweet. This is today off the internet. The ship carrying the coating chamber is actually en route now to Chile, which is pretty exciting. So it's a big thing. It'll scan the sky fast, but it moves really slowly on the ground and on the water. So this is really exciting. Why LSST? You know, what is the big paradigm shift that we're going to have to encounter? Well, we go from photographic plates. So this is I love this because I'm a pre-WMAP scientist, which means I'm definitely a post-SDSS scientist, and so we forget what it was like in the good old days when we had photographic plates, and so this is a digitization of a photographic plate, and we're going to concentrate on just this galaxy. Surveys like the Sloan Digital Sky Survey, now unfortunately this is a little bit lit up the screen, but you can see that it gives a much richer picture, and of course Sloan's covered a large fraction of the sky, which is why it was so revolutionary. Also, Tony Farrell was my undergrad lecturer, so I was very pleased to see Tony's work on the screen. But Tony once said that 2DF did all of his science, which had taken him 6 or 7 years, in 2 weeks. So it's amazing the revolution that speed can make. Now, if we want to look at the types of depths we can expect with LSST, this is an image from the Deep Lens survey, which will go to similar depths as LSST, but of course it was on a tiny patch of the sky. And so this is a simulation of what we think LSST will get, which will be that depth, but over the whole sky. So 37 billion stars and galaxies, 10 million alerts, thousands of pairs of exposures, separated by 15 seconds, and terabytes of data. And these numbers just are astronomical. Sorry. Okay, so LSST has two different surveys. They have the Wide, Fast, Deep survey, or WFD, and then the deep drilling fields, which are those small blue patches that you see. And they're designed with different science cases in mind, and one of the things that I was particularly interested in is what will LSST do for supernovae and supernova science. So if you think of going to depths of, 25th magnitude in the Wide, Fast, Deep, and more like 28th in the deep drilling fields, that's pretty revolutionary. If we try and compare LSST depths to other surveys, because that's a useful thing to do, you can see here we can compare surveys that existed previously, so SDSS, for example. So we have band on the x-axis and 5 sigma depth on the y-axis. And you see that Sloan was sort of around 22nd, 23rd. LSST, the Wide, Fast, Deep, will go a little bit deeper in the G-band. But the key difference, if you look at this plot, you don't necessarily think that LSST is going to do better than other surveys unless you look at the deep fields. But then you go over here and you look at the survey area, and it's really blowing everything out of the water. However, if you look in the middle, you'll notice this is a problem. So this is the single filter gap, which if you care about static science is not a problem, and if you care about transient science, to have 20-day gaps between filters is a bit of a problem. Euclid should, this is an American plot. Euclid should be on this plot. I will, yeah, exactly. Whoops. Can we fix this plot by adding Euclid and optimizing LSST? So at least we are optimizing LSST with Euclid in mind, but you'll have to wait a couple of slides. So this is a plot by Dan Skolnick, putting into context various observations. Now, there's a lot of analysis that was done and talked about this time on the JLA, the Joint Likelihood Analysis, the collaboration, the huge collaboration between the Sloan Digital Sky Survey Supernova team and the SNLS Supernova team, which was really, really important because it helped us retrain the models that we were using to fit and model the population of supernovae, and that was really important. But if you actually look at the redshift range, that takes you, to redshifts of about just shy of 1. And then you have the HST supernovae that fill in the higher redshift. And then you have this critical group at low redshift that are anchoring your Hubble diagram. Again, this plot is a little bit old, but we add a few photometric surveys in addition to the spectroscopic ones. So Pan-STARRS had around 5,000 supernovae, and then also the Foundation survey led by Ryan Foley added about 800 to the low end. Critically, LSST is expected to add around 400,000 in this intermediate redshift range, so the orange band going up to around redshift 10.7. Now, 400,000 supernovae it's wild. It's just so many supernovae. And so one of the things we need to do is figure out how to handle that. So I am a co-chair of the DESC Supernova Working Group, and I wanted to just highlight in a little bit of a schematic what kind of things we care about. Okay, so what are the questions that we want to ask in any supernova survey? Well, can we find supernovae? Can we classify them? Can we measure the distances? Can we constrain properties about the hosts and the environment? Can we constrain our systematic errors? And then can we actually do cosmology without redshifts for all of these objects? So we're trying to tackle all of these. We have finding supernovae, we're looking at survey optimization, I'll talk about that a little bit. Classifying, I'll talk about right at the end. Measuring distances, there are lots of work being done, particularly in Paris, actually, on light curve modeling of supernovae. Lots of my colleagues at various labs are involved in that. Can we optimize follow-up observations with other groups? And so again, this is something that requires a worldwide participation, and it's not necessarily trivial to figure out how to do that, because not everyone wants to spend all their time looking at supernovae. And then there's sort of a difference between can I get a host redshift or can I do a live follow-up of a transient, which requires target of opportunity. Can we constrain systematics? I never thought I would spend my life so excited by systematics, but here we are. And can we do photometric cosmology? And I'll talk a little bit about some of these issues and why we care about them. But I think this is important because if you focus on one thing, if you only care about the physics of supernovae, then you might design a survey that optimizes for a very particular science case. And we want to make sure that we bring people along that want to do different things. Okay, so finding supernovae requires us to optimize our survey strategy. So this is a simulated deep drilling field object, and you can see the red line is on the points, so that means it's reasonably well fitted, which is great. And this is from a previous version of the LSST observing strategy simulation. But we got a bit of a shock, at least I got a bit of a shock, when I joined LSST and I saw that this was a proposed wide, fast, deep supernova. So you can find it, but you can't really do anything with that, right? Cosmology, you'd get a huge error on your distance modulus, and so it'd be really difficult to do science with that. And so we started waving our hands a lot, and just released very recently is the LSST white paper effort. So white papers to coordinate the survey strategy. Now, this is not a transient-specific effort, and in fact, it's a public effort. So anyone who is not even involved with LSST can propose to write a white paper about something that you care about. And the way this works is that there's a little bit of a learning curve because LSST has generated what they call operations simulations. So these are databases that contain information about the right ascension, declination, time of day, seeing, cadence properties, and so then you use that to forecast your science case. Within the Dark Energy Science Collaboration, this work is led by Michelle Lochner, who is at Ames in South Africa, and Dan Skolnick, who is just about to start his faculty job at Duke University. And so he's compiled a initial sort of look as we start running our different simulations. So I've been running countless numbers of supernova simulations, but we really, as part of the Dark Energy Science Collaboration, have to do something a little bit more difficult. Now we have to balance transient science with static science. And so what are the kinds of things that we look for? Well, you want a wide field, and you want it to be reasonably evenly sampled if you care about static science, if you want to learn about statistics. We want to make sure we have a little bit of our fields that can do follow-up of things like gravitational wave sources. We want to make sure we have a large number of supernovae, so around 300,000 well-sampled supernovae in the wide field, and then 5 of these deep drilling fields that will do really, really well and give us our gold sample and overlap crucially with amazing experiments like Euclid, of which I'm actually a part as a Canadian member, but anyway, that's another thing. And also WFIRST. In addition, we want to make sure that the survey strategy has the right kind of cadence in all the bands so that we can enable a good science case and also look at things like strongly lensed supernovae, get a sample of around 100. So these are quite a lot of goals and requirements. And so Dan and Michelle are doing the heroic task of taking all our individual requirements, which go from, I'm doing the dark energy figure of merit, but some people are doing just the numbers of supernovae discovered or the numbers of strongly lensed sources, and then combining them all into recommendations. If you care about anything in particular, you as an individual can submit a paper by November the 30th. Okay, but one thing we can do is ask a different question, which is, what is the conservative analysis that we could do today? And how do we place bounds on systematics? Now, again, I think this is quite important, and it goes to Leach's point today. If we just do an analysis, and I'm watching the step, if we just do an analysis and then present our results, someone can turn around and say, I don't agree with any of your systematics, and I'm going to throw your results out the window. So we were trying to take the other approach, which is to list all the systematics that we think we have, talk about the ones we know how to handle, and mention the ones that we don't yet know how to handle, or that we just aren't yet. And so if you like to read a document that is 30 pages long and has 60 pages of an appendix, it's on the archive at the moment. It's the Dark Energy Science Collaboration Systematics Science Requirements document. And the take-home message of the plot is the following. We combined individual science cases together and then also applied a prior to get this final figure of merit, which is around the 500 mark if you include statistical and systematic uncertainty, which is pretty great. But then we asked ourselves if that's the target that we think that we'll do, if we allow for, I should actually make this a little bit clear. We allow for different kinds of systematics. So we define 2 kinds of systematics broadly. Calibratable, which means things I can control, and those include things like the 0 point of the filters, or the uncertainty in the band positions, or the calibration if you're doing calibration to some standard star, that calibration. And then we also talked about self-calibrated systematics. And those are systematics that include intrinsic alignments if you did weak lensing. In our case, it includes an evolution in some of the fit parameters, for example, with redshift. These are things we know might happen. We're not entirely sure how we couldn't remove them, and so we try and include them in our uncertainty so that we're not being too optimistic too early. Because if you crush your dreams early, then you're always surprised. Sorry, that was a joke. And this is the one for supernovae, but in fact, each probe in this document has their own image, and you'll see the green are the things that I thought we could handle right now, and the gray are the things that we don't yet know we can handle, or we have a path to handling them, but we haven't actually done them right now. And they include 2 important things, which I won't discuss in much detail, but will highlight a little bit. And the one is redshift uncertainty, So in our analysis, we're assuming that there was some other survey that did host redshift follow-up of 100,000 objects in the wide field and about 2,500 objects in the deep field. But of course, that is grossly underutilizing our data, and I'll talk a little bit about that at the end. And the other thing is classification error. We didn't include, which is something really close to my heart, we didn't include the uncertainty that you may get classification of the objects incorrect, and I'll talk about that as well. Okay, so this is what we have. Again, we use a simulation package developed, I used a simulation package developed out of the US called SNANA, which allows you to go from cadence and then also lots of different assumptions about models to simulate these supernovae. For now, we just assumed 1As only, but in fact, we know that the universe will contain very many other transients, so wait until the end of my talk. And so this is the kind of approach that's followed in systematics for supernovae. You know that you have some offset, you simulate one model without that, one model with that, and you figure out what is the bias in mu that you would get from your cosmology. Now you can either just blow up your error bar by that value, or you can include a bias vector and marginalize over it. And so what we did was we said, if we made the incorrect assumption about parameter x and got a different distance modulus, let us assume that our mu is biased. What is the biggest shift we can tolerate in W0 and WA, assuming that we don't account for it in our error bar? So why is this so important? Well, I wanted to show you, this is one plot of our error bars as a function of redshift, which, I mean, you know, they look rather big. There are two models here with W of minus 1.1 and 0.8 and minus 1.05 and 0.2. Okay, maybe you think those models are very different anyway. But I just want to take you back to the plot I showed you before, and I want you to concentrate on the y-axis. So this is the difference in distance modulus between your data and some model in magnitudes. And now I want you to take you back. This axis is in millimagnitudes, so it's intense. Where you can't even plot a distance modulus the way you normally see it as a curve, because the error bars are so tiny that it's just uninformative. So we really are, with 400,000 or 100,000 supernovae, there's no wiggle room left, and so that's why it's so exciting and so scary. Okay, so these are the kinds of plots that I made. The y-axis is showing you the bias away from your fiducial point in the W0, WA space as a function of the error bar. The error bar assuming only a self-calibrated or intrinsic systematics. And what we want is that you can imagine if you go up to 1 on this graph, you're 1 sigma biased in units of this sort of area of the ellipse. But because we have all these systematics that are adding in quadrature, and we have a couple more, we realized we didn't want this to be more than about 0.3. And so year 1, we're actually okay. So the x-axis shows how much do I have to scale a systematic by, so some kind of arbitrary value to begin with, but I scale that down, and how much better do I need to know it? And we don't need to know the Milky Way extinction law any better than we do now, because we never crossed that line. Similarly, the calibration is okay. Then you go to year 10, and suddenly we're in trouble. One of the things that you'll see this line shooting right off the page is something we know really well. We need to do the same kind of analysis that was done in JLA, which is retraining the light curve models that are used to predict the distance modulus from the light curves. We have to do that on day 1, and we know that, which is really exciting, and this sort of confirms that there's really no time left to waste. I mean, we have 10 years, but still. Okay. And so this is just put in for the other systematics in a little bit more concrete terms. So we can tolerate a systematic uncertainty in the mean filter wavelengths of the individual bands of not more than 1 angstrom. Okay, great. And also we cannot tolerate a systematic in the 0 points of more than a millimagnitude. So we have our work cut out for us. And this involved a lot of interaction between the LSST project, which designs the telescope, and the science groups, which say this is what we can tolerate before our science case sort of loses that dark energy task force figure of merit. It's particularly hard because, of course, the dark energy task force, as prescient as they were, they defined an arbitrarily large sample of supernovae that we would achieve in stage 4 with almost no systematic errors. So we're having to make sure we live up to their dreams. Okay, so what's next? Now that we've done the most conservative analysis that we can with tools that we can do today, which includes very, very simple likelihoods, how do we look to the future? Well, this is actually something that I've been interested in since my very first paper, which was just asking, what do you do with a large photometric sample where you don't have confirmation that all the points are in fact a type 1a supernova? And in 2012, we tried to apply this approach to SDSS, and of course there really weren't enough supernova to make a huge impact, but this is a simulation that we ran just to show what I mean. So in this case, the color bar is showing you the probability that the point is a type 1a, and you notice that, oh look, there's this band of points around that go exactly around the cosmological model, and then there's this other population of objects that we know are not standard candles, so there are 1BCs and type 2s that have this offset. And we wanted to say, can we use a statistical approach, a Bayesian approach, to do this? Now again, a word of caution about working with new fields. The first paper we wrote on this was in 2006, and it was just a Bayesian mixture model, a Gaussian mixture model. And so any statistician that I spoke to, said, that's great, it's totally trivial. And yet at the beginning, I was told by people in the supernova community that it's magic, you don't understand it, it's a black box, this is weird. And so it took a long time for the community to actually kind of jump on board. This is just showing the same thing, which is if you just average over that distribution, you'll get the wrong answer, basically. And so we applied this to simulations and to the SDSS data, and showed that if you just followed a procedure where you say take all the points above some probability value, and then you did some outlier clipping, you could introduce major biases. Other approaches have been followed by folks in this SDSS group and others now that these kinds of methods are catching on, but they involve kind of color cuts to make sure you're only selecting a sample that looks really like the one as before. And again, that's great if you know the model, and if there's too much uncertainty in the model, it can lead to a lot of biases. And that is just I forgot I have a clicker. That's just the Beam's formalism, which is just really, can you marginalize over, for each object, you have a likelihood assuming it's a 1A times the probability it's a 1A, and then a likelihood that it's a non-1A, which includes additional sources of shift or the spread in the distribution, times 1 minus the probability if you have just a two species model. So Beams has been applied to the pan-stars data. So this is a paper by David Jones, and you see this really awesome plot that he made where he shows, a low redshift sample where they have spectroscopic confirmation, and then a high redshift sample that includes both 1As that have been spectroscopically confirmed and photometric objects, so they're not sure. And you can straight away see, look, there's this scatter, but there's also a little bit of bias, and so you want to make sure that you do your likelihoods kind of consistently. Similarly, Beams is being extended by some colleagues, so this is work I did while I was in Cape Town working with Bruce Bassett, and so his group has continued to expand upon this, adding things like Z and including things like redshift error as well. And this is something that I continue to think about as well, and in fact, before there's a shout out to another paper. So you could say, instead of thinking about the type problem, which is what I presented with Beams, how do I include supernovae if I'm not sure what type they are? You could say, well, I don't really care about the photo redshift problem. I'm just going to use the fact that my photometric sample will overlap with a spectroscopic sample, and then I can use the well-known techniques of cross-correlation to extract the cosmology that I want, because we think that the supernovae are traces of structure. So this is a slight different approach, and in fact, it's something that I'm looking at with a student of mine, to use supernovae as tracer of peculiar velocity. But Suvadeep and Ben has showed that you do really well with some assumptions, some optimistic assumptions about what LSST can do. And in fact, one of the first tasks when I get back from this meeting is to incorporate these kinds of ideas, but actually in the full simulation of supernovae. Because one of the worries that we have is, this is assuming that the only place that your supernova hurt you is the likelihood. But of course, the supernova redshift goes as a prior into the fitting procedure. And so you can mess up the fits if you're not careful. But I think this is really exciting stuff. And so one thing that I'm working on, since everyone is putting up graphical models, I'm working on with a student, Alex Maltz. This is actually their photo on the internet, so you should hire them. They're on the job market this year. And my postdoc, Tina Peters, and we decided to try a new acronym because acronyms are great. And so we came up with SCIPPER, which is Supernova Cosmology Inference with Probabilistic Photometric Redshifts. And here you're actually doing two things. So people like Tina care a lot about photometric redshift in and of itself, and we care about sort of the supernova problem. And so what you can do is you can realize that you have a combination of things. You have what the universe actually gives you, which is some cosmology parameters, some parameters that describe the type proportions, and then you have selection functions. And then what you want to do is actually build up posteriors, one of which is related to your likelihood fitting, and one which is related to your photometric redshift estimation from something like a host galaxy. And then those become your joint posterior, where you're really constraining both redshift and supernova properties. And this is something that we, so I've just expanded on these. This is something that we're simulating now. We're trying to play a slightly agnostic approach, which is simulating data that simulating the posteriors that actually come out of a light curve fitter. So we're not doing the light curve fitting separately to the host galaxy fitting, but we're assuming realistically what would the joint likelihoods come out of from those different fitting procedures, and then using that, thank you, to fit cosmology. Right, and so these are the different types that come together, and then you have a full joint posterior that really takes into account that light curve parameters and galaxy colors, and those allow you to do things self-consistently. So watch the space for this paper. The interesting thing, though, is if you follow this kind of procedure, then the idea of having a Hubble diagram, which we all look at, goes away, because there is no Hubble diagram anymore. You really go from something like this to something like this. So we talk about the sheet cake, where first of all, you have sheets depending on the type of the object that you assume. In this case, we're assuming that there are 3 types of objects. And so you have a posterior that's in a sheet for each object. And if you wanted to project out a normal Hubble diagram, you have to integrate over redshift uncertainty, you have to integrate over type probability to get these different Hubble diagrams. And so one of the fun things about this, along the same lines of trying to speak someone's language, is projecting out the SCIPPER sheet cake in different ways to try and address people who care about galaxies and not supernovae, or supernovae but only 1As, or supernovae that care about probabilities. Because really in the end, you don't have that simple Hubble diagram in the same way. Okay, so how will systematic analyses play into the future? So I mentioned that we have this systematics diagram, and that I have sort of ignored redshift, and we've ignored classification. But classification is one of the big problems in transient science, and we had a great talk today about supervised and unsupervised learning techniques to identify different kinds of, to classify different kinds of objects. And so these are some techniques that were tried about 8 years ago now in the Supernova Photometric Classification Challenge, which I participated in, and there were people that did a combination of supervised learning, template-based methods, unsupervised learning, and we all submitted plots like this. We were trying to maximize some space of efficiency or purity, and this was focused on a DES, a dark energy survey, like survey, and we didn't win, but that's okay. And one of the things, so the approaches included things like feature selection. So we fitted a parametric form to the light curves and then used the parameters of those fits in our fitting procedure. People like Emily Ishida, who is here in France, did things like principal component analysis with PCAs. And then more recently, after the challenge, Michelle Lochner took a bunch of different template extraction techniques and ran them on the public SNFOTCC data to see how people performed, and compared different machine learning techniques as well. So what we found, perhaps unsurprisingly, is that every method struggled with non-representative data. What do I mean by non-representative? I mean that we do spectroscopic surveys and get a small sample and train the algorithms on those. And then we do huge photometric samples that have different depths and different properties. And everyone said at the end of the challenge that we were all complained because our algorithms were terrible on the non-representative data. And so we decided, in order to fix that problem, we would just face it head on. So So enter 2018. So I'm with Rick Kessler. I'm the PI of Plastic. You can tell acronyms are a big thing. This is the Photometric LSST Astronomical Time Series Classification Challenge. So it's just been hosted on Kaggle. And if you are a statistician or an astronomer or a data scientist and you want to win between $8, $12, or $5,000, because there are prizes associated, you should take part in Plastic. So if you go to kaggle.com and look up Plastic, you'll see this challenge. And what is it? So we wanted to make a classification challenge in a similar way to what we'd had before, but we knew that we had only a couple of types the last time. So the first thing we did is we put a call out to the community, and we said, if you have an interesting model of a transient, come and speak to me. Now, if I told you what models were in there, I'd have to kill you. But we collected many more models, about 14 models that you'll see in the training data set. We simulated an LSST type cadence. We did an extensive round of data validation to try and make it just hard enough that you want to tackle it and just easy enough that you don't stop tackling it. So as of the competition launched a month ago, and we have 310 teams, which is amazing, and I think only 2 or 3 astronomy teams. So we have a lot to answer for. But Kaggle, I wanted to highlight some of the people who are really on the phone with me twice a week as we looked at the data, and particularly Rick Kessler. So Rick designed the software SNANA and has put in, a whole extra job of person hours just to do this. You can see a note that we put on the archive which describes the data, and it's written explicitly to be not domain specific. So we roughly explain things like redshift. We talk about the bands. We talk about how observation gaps make it difficult to find things. We also have a GitHub starter kit. So Gautam Narayan, who also should have a hire me sign, he's applying for faculty jobs and is incredible. And again, Emily Ashida worked really hard on this starter kit, which both goes through talking about what the data are, and then also tries to explain to people in the community what we've tried in terms of classification. So this is a breakdown of all of the features that you might take away from a certain data set, and you just see how are they correlated, are the different bands correlated with each other, partly as a way to kickstart people to try new methods that we haven't thought of, because the goal with this is to get people excited enough so that we can actually learn about how to do classification better. But we needed to figure out how we can evaluate between them. And so working again with Alex Maltz and a bunch of other folks here who didn't make it onto the slide above but are involved in all of the processes, we decided to look at designing a metric. So rather than just say, I want to find a type 1a, which not all of the community cares about, we wanted to say, can we design a good metric that handles typical ways you might have a systematic or typical ways your classifier might work, and that we balance well over classes and types so that all your science cases, if you care about AGN or you care about supernovae, you'd be able to get a good result. And so this is an example of ways your classifier could behave. So the X and Y are the true class and the predicted class, and we're assuming that you're returning a probabilistic classification in order for us to do our job. And you might say, look, I do really well if it's a type 1a supernovae, but I don't know how to do anything else. Or I actually only care about supernovae, so I'm just going to assume everything is a supernova. I'm going to always classify it as a supernova. You could be perfect, but let's face it, no one's perfect. Or you can say there's some characteristic of one object that I always think it's the other one. So I get everything right, but I actually mess up one of them, and I assume either things assumed to look like me, or I assume something is something else. And so what we did is we decided to generate a bunch of different classification attempts where we varied the numbers of objects, and we said, okay, these are the stars are the true type, and we took a draw from the kinds of distributions you would expect if you had these systematic biases in your classification. And then we decided, well, let's evaluate the way our metric might proceed at seeing if you did badly. And so in this case, we looked mainly at 2 metrics. In the end, for the challenge, we settled on the log loss, which basically has a weight which includes the numbers of objects in the class, so you really have to do all objects equally well. And then we have an additional slightly hidden weight in case one object is more important to you than the others. Interestingly enough, that weight we hid from the community, and I think it took 24 hours for the Kagglers to figure out what our weighting scheme was, which is scary. And so this plot is a little bit complicated, but what we were trying to say is, as the number of objects that you'd got wrong changed, how did these metrics behave? Because what we're really interested in asking is, I want to be able to have you not game the system. So if you decide to do cruise control and classify everything as one type of object, I want you to be penalized. Because the thing I care about is making sure you do well at classifying all objects. We also have additional science prizes for people who do really well at classifying one object, but we really wanted you to be able to do well on everything. To make it a little bit more complicated, we've decided to, again, mimic nature. So the data are very non-representative. We have a training set of around 8,000. We have a test set of around 3.5 million. We have 15 classes that you have to give answers for, but we only give you 14 classes in the training set, which means there's one class that we ask you to label as other, which is there something cool or weird that you haven't seen before? And we're not even telling you how many different types of classes could make up that other class. Again, this is trying to mimic the way life is in astronomy. We think we might find new things in the sky that we haven't seen before. And so you should definitely get engaged and take a look both at the metrics paper, which is on the archive, and at the data itself. Okay, so hopefully I've at least given you a flavor of the kinds of things we care about in supernova cosmology and transient science in general, and I've highlighted the fact that you should be thinking about sheet cakes and not Hubble diagrams. You should be both scared and pleased that we know about some of the systematics in the dark energy science collaboration that we're going to undertake, but we also have a lot of work to do, and hopefully you are about to sign up to be a member of the Plastic Classification Challenge. Thanks.